Hello, and this is a video basically on CorePure1AS, which was an exam which was sat a couple of days ago, 16th of May 2022. I'll tell you straight away, my impressions of this exam are, that's tough, really tough. Firstly, the reason why it's tough is mainly because Edexcel are going crazy for modelling questions, really crazy for modelling questions. And they're the really tough questions. I think they're particularly difficult to do in exam conditions. And certainly they've set questions which are a lot more straightforward than these before. Anyway, let's, without further ado, let's have a look at what they set. Now, question 1 wasn't too bad. Now, it's not too bad because you've got this AB minus 3C plus KI equals 0. And the 0 matrix is 0, 0, 0, 0, 0, 0, 0, 0. And so first thing we're going to do is times A by B. Now, just to remind you how to do this, personally, in an exam, I'd probably just pop this into a calculator, and I think that's what they want you to do because you can get the answer straight away very quickly then. But just to explain quickly how we do matrix multiplication, we're going to do A times B, and so to work out the first element, we're going to do 4 times 2 plus minus 1 times minus 1, which is 9. To work out the second element, you're going to do 4 times 3 plus minus 1 times 6, which is 6. To work out the top right element, you're going to do 4 times 2 plus minus 1 times 5, which is 3, and so on and so forth, and you get that matrix there. That's what I did first, and you can see actually my work down here on this page. So I worked out AB, and then I trebled C, so I trebled all those values, and I took it away from AB, and actually originally I think I had 22, 0, 0, 0, 24, 0, and 0, 0, 24. And it was when I didn't have exactly the same numbers here that I realised I'd made a mistake in my multiplication, and that I should have used my calculator. Okay, so what do we need to add? What multiple of the identity matrix do we need to add to this to get 0, 0, 0? Well, minus 24 will do the trick, because minus 24 times by the identity matrix I cancels everything out, and we get 0. So that's quite a nice easy start actually, not bad anyway. Now, this is a bit tougher though, because I can see why students might miss this. Why is there no constant such that BA minus 3C plus MI equals 0? Well, firstly, if you try and work out BA on your calculator, you're going to see that you get a 2 by 2 matrix. Why is that? Well, whenever you put matrices together and you try and times them, you won't be able to multiply them unless these numbers are the same, unless the column in the matrix on the left is equal to the number of rows in the matrix on the right. It's always rows, then columns. So these are conformable, and the resulting matrix will be of this size, the rows in the first matrix and the columns in the second. Now, if this is 2 by 2, that is a problem for a number of reasons. Firstly, C is 3 by 3, and you can't do 2 by 2 minus 3 by 3. They have to be exactly the same size matrices if you're adding them or taking them away. Also, they said that I was defined to be the 3 by 3 identity matrix, so there's another good reason. And so there we go, that's not possible because BA will be 2 by 2 matrix, but I is 3 by 3 and 3C is 3 by 3. Okay, for B part 1, I'll show how matrix C can be used to solve the simultaneous equations like this. Well, I'm sure you've seen this set up before. You just need to have the coefficients set up as a matrix, times it by x, y, z. You're going to get that first equation because minus 5 times x plus 2 times y plus z is minus 14. There we go. And so this encapsulates the information. And now, in order to get this right, we need to pre-multiply both sides of this equation by the inverse of C. And that will give us x, y, z, because if we pre-multiply by the inverse of C, c to the minus 1 times c is, c to the 1, well, is the identity matrix, yeah? And if you times the identity matrix by any vector, you're just going to end up with the same vector. It's like 1. It functions as 1 for matrices. And so, yeah, you end up with just x, y, z equals inverse of c times minus 14, 3, 7. Now, I'm rubbish with calculators, and I can key things in several times incorrect, as you can see down here. So I eventually got the right inverse of c, and I'm just going to multiply that by minus 14, 3, 7, and then you get the answer there, yeah, and I checked that. Now, I think it's really important in this paper to note how many times you can check things, because some of the answers are really tough, and so you want to be able to check your answers. You can easily check this one, because your calculator solves 3 simultaneous equations and 3 unknowns. So check it, yes I did, and you should end up with those values for x, y, and z. Actually, I think I might have checked it just by casually putting it into one of the equations, but you can check it by solving it simultaneously on the simultaneous equation solver. So that was question 1. Hopefully that one was one which you got right. It was definitely one of the nicer questions on the paper. Now let's have a look at question 2. And I wanted to show you this page just because you can see some of the passive-aggressive feelings I had when I started drawing the diagram. I then drew it out nicely on the next page, but I haven't scanned that in. Now this wasn't too bad either, this question. I think when you see something like that, which is in Cartesian form or A plus BI form, then you want to put it in modulus argument form. There's lots of ways you can do this actually. Drawing a little picture out would be nice, but personally I just took 8 straight away out of it because I know that root 3 over 2 plus, squared plus a half squared equals 1, which square rooted to 1. So I knew that basically that would just give me immediately the modulus. But you can work it out the long way by all means by doing that square plus that squared square rooted. That's 48 plus 16, you get 64 square root, you get 8. And then I've drawn a little picture to work out the argument, and I've just gone, well, we're going root 3 over 2 across, a half down, and therefore I can work out theta. I mean, you might want to use soccer tie trig, but I know these ones. Well, tan theta is a half over root 3 over 2, which is 1 over root 3. Inverse tan, you get theta is pi over 6. But I've got it as minus pi over 6, and that's for the very good reason that we're going underneath the x-axis, and so we need a negative argument. And so w equals 8 cos minus pi over 6 plus I sine minus pi over 6. And remember, if you key that into a calculator, and you can check it if you like, you will get that. So that is something you can check. Okay, part B. Represent w in an Argand diagram. Well, that's easy. Just 4 root 3 across minus 4 down. But then represent this. Now, I hope straight away you see this is one of those half lines. And I hope also that straight away you turn it into arg of z minus 10i. Yeah, so that you can see it's actually a half line which is 60 degrees above, or pi over 3, above the horizon, and it's going to start at minus 10i on the y-axis, if you like. So let's draw these, because you do need to draw it because it massively helps you for part C, which I think is pretty tough. Okay, so I'm going to try and draw this as neatly as I can, which is probably not very neat at all. Now, 4 root 3 minus 4i. There we go, there's w. Yeah, that's not a problem. However, if you actually work out, because we've got to draw a half line on here, I really want to decide if it's above w or below w, because that's going to make a massive difference to my final answer, to my final question, which is, sorry, I lost on the screen here, find the minimum distance of w from this half line, which is going to be like a right angle triangle thing. We really need to know if this is above or below w, which means what I'm going to do first is I'm just going to point out that we've got a, well, let's show you. Let's just quickly work out this angle here, yeah, and compare it to 60 degrees. Well, that angle there, as that's 4 root 3 across and that's 6 up, yeah, you can do tan theta is 6 over 4 root 3, and it comes to 0.714. Now compare that to pi over 3, which I guess roughly equals 1, because pi is roughly 3, but it's a little bit more than 3, so it's slightly bigger than 1. This angle is smaller than 1, and therefore, as this is the angle of w and this is the angle of the half line is actually going to be above w, passing above w rather than passing below w. I will use all those values in a second, but I just wanted to, let's just get the rubber so I can just try and neatly draw this half line. So all you need for part B is w clearly labelled, and I guess some kind of, let's do it as an arrow actually, some kind of half line. Oh no, I hate it with curves like that. Never mind. Alright, I'll just do it as a straight, but oh no, that's not working either. Alright, I'll just hold my pen very steady. Sorry. You're probably getting a bit fed up listening to me, unless you're in my class where you're probably used to this. Okay, so this is the arg of z plus 10i equals pi over 3. And like I say, I can tell that by comparing the angles. Now that's going to come in really useful because I need to find the minimum distance of w from this half line, yeah? Well, if I'm going to work that out, then I need to know a few things, because the minimum distance is going to occur when that's a right angle, and that's the shortest distance from a point to a line. It always occurs at the foot of the perpendicular, which means I need this angle, let's call it alpha. Now, we've already discovered just a second ago by doing the 6/4√3 thing and tanning it, that this angle theta was roughly equal to 0.714. And so I can find alpha now, because alpha is going to be pi/3, that's the angle the half line makes with the horizontal, minus theta, yeah? And now what I can do to find the shortest distance, I can quickly find this side by Pythagoras, 6 squared plus 4√3 squared square rooted, comes to √84, and then I can say, okay, sine alpha is x over √84. And so I can find x by doing √84 sine alpha. Now I kept the exact value in my calculator, and it ended up being 3. And I thought, well, that's just too nice a number. There's probably a nicer way of doing it without using ugly values, like, but yeah, that's what I did. I just worked out alpha as pi/3 minus this. This ended up being 0.714, I think, ... But after you do it, it exactly comes to 3. So I felt quite confident with my answer there. It just seemed too nice to, to ignore. But there we go. But as you can see, I like to include this because it shows you sometimes, yeah, we all get annoyed and stressed out. We realise we've drawn the diagram wrong. So you just draw it again. I mean, I'm quite a messy mathematician, really. You can ask my class, people in my class, they'll tell you, very, very messy. Okay, so there we go. That's that one. Let's try and get half this paper done. So we'll do a couple more questions and I'll do another video for the last 4 because I'll need, I think, a stiff drink to actually get through those. Okay, here's the next one. Okay, right, this one was interesting. Quite like this one. Preferred this one, probably one of my favourite questions on the paper. Firstly, they gave you the way you rotate in 3-dimensional space, and I think that's fair, actually, because it's quite difficult remembering those. These are all in the book, aren't they? But they've given you this one, which I think's quite fair. And the first thing they've said is, okay, we're going to reflect P, we're going to reflect it in the plane y equals 0. Now I have great fun pointing out to students that, like, the line y equals 2x, in 2 dimensions it's a line, but y equals 2x in 3 dimensions is a plane. It's the same with y equals 0. In 2 dimensions that's a line, but in 3 dimensions it's a plane. It's like a mirror. Now it wants you to write down the coordinates of Q after reflecting in y equals 0. Well, this is what I actually did. I actually drew a picture, yeah, because I wasn't entirely convinced at first, but like this XZ plane, I'm drawing Z up here and Y is going through the page. That's like, the flat page, and Y is going through the page, and if you reflected it in a flat page, you'd end up with all your positive Y coordinates turning negative. This is exactly what happens if you reflect in the line y equals 0 as well, actually. The line y equals 0 is the x-axis, and if you reflect in the x-axis, all y coordinates go from positive to negative. So if you kind of guessed at that one and thought, oh, it's the y's which change because that's what happens in 2D space, you guessed right and you did well. So all I've got to do here is change the y coordinate to negative on P, and therefore Q is 8 minus 3, 2. Okay. Point R is the image of P under a transformation rotation through 120 degrees anti-clockwise about the y-axis with respect to the right-hand rule. So, oh yeah, and I could waffle on about this right-hand rule bit, but I won't actually at the moment. I've had conversations with students in my class about it does matter which way your perspective is in these. But anyway, determine the exact coordinates of R. So we're rotating P 120 degrees. Well, we've obviously got to multiply it by this matrix up here. And I'm just going to plug in 120 in, making sure my calculator's in degrees, and work out what the matrix is. Then I'm just going to times it by this, and I'm going to be really careful. I think I did this in my head, so there's lots of room for error here. Minus 4 plus 0 plus √3, minus 4 plus √3, 0 plus 3 plus 0, 3, and then minus 4√3, 0, minus 1, minus 4√3, minus 1, and so I get that. I think I've done that right. Looks good on second inspection. Okay, so that was exact coordinates of R. So that's, I probably should have labelled that equals, OR. That's the vector anyway to get to OR, but the coordinates are obviously just that vector on its side. It's a position vector. So yeah, maybe But if I was being really paranoid in an exam, I would be really paranoid, just in case the nasty examiner wants to take a mark off me here. There you go. There it is as a coordinate. Now leave me alone. Okay, so we've got R. Now we've got to find PR. Well, that means we've got to work out the vector PR. And here we're going from OP to OR. Here's OP. Oh no, that's OQ. Sorry, let me write down OP. OP was 832. I probably did this in my head. That's the thing. OR is that one. Now PR is going to be OR minus OP. Yeah? So I need to do minus 4 plus root 3 minus 8. That gives me minus 12 plus root 3. I need to do 3 minus 3, which gives me 0. And then I need to do minus 4 root 3 minus 1. Take away 2, which is minus 4 root 3 minus 3. And then I can work out the length of PR as a simplified surd. So I did that squared plus that squared plus that squared. And you know, I always wonder how much I have to show now my super duper calculator does everything. But this should come to 144 minus 24 root 3 plus 3. That should come to, I've written this down wrong because I suddenly realised I did it wrong and had to get rid of the 36 because I made a mistake earlier. So then we've just got to do 48 plus 12 root 3 plus 12 root 3, so that's plus 24 root 3, and then plus 9. And then let's check I've added this up right now. So what have we got here? Well, 147 plus 57. 147 plus 57 is 204, square rooted, and so that comes to 2 root 51. I don't think I can simplify that further, can I? Because that's 51 17 times 3, and they are both prime numbers, so they can't be roots or anything like that. Okay, so I think I've got that one right. Let me know in the comments if I make any mistakes in this, because it certainly wouldn't be the first time I've made a mistake. No way. Show that PR and PQ are perpendicular. It's a bit of a funny question, this, isn't it? So PQ was just 0 minus 6, 0, because if you remember, Q is 8 minus 3, 2, and P is 8, 3, 2. So how do we get from P to Q? Well, if I've got to get from 8, 3, 2 to 8 minus 3, 2, I think I've just got to drop 6, yeah? And so it's 0 minus 6, 0. I don't need to touch the X or Z components. And so PR dotted with PQ, well, you're going to do that times that, plus that times that, plus that times that. And so you're going to get 0 plus 0 plus 0, which equals 0. And therefore, they're perpendicular. That's how we prove two vectors are perpendicular in, well, using the dot product in this particular module. Okay, hence determine the exact area of triangle PQR, giving your answer as a surd in its simplest form. Okay, I just drew a little picture here. PR, PQ, I know the right angle's at P, because PR dot PQ is perpendicular, so the right angle must be there. PR was 2 root 51, PQ was 6, so I've got to do a half times 2 root 51 times 6, so I make that 6 root 51, and that's the exact area of the triangle. And I've got my answer as a surd in its simplest form, I believe. Let me know if you think I've made a mistake on that. I'd love to hear it. Okay, let's do one more. Let's do one more. Page 4. Let's see what this was all about. I can barely remember what it is now. Yes, the roots of the polynomial one. Now this one, at least it's not a modelling question. That's what I'll say in its defence. And it does have some easier bits, but I think the last part's really tricky. And that's why I actually did the last part in 2 different ways, just to check my answer. But you haven't always got the luxury of time, though, under the new syllabus. Like I keep talking about the new syllabus. I just think back, because I'm quite, you know, I've been teaching a while now, and I think back to 2017. 2017 and further back than that. You know, this would have been regarded as a difficult question then, definitely one of the harder ones on the paper. But now this is actually not so bad, even though it's still really quite a tough question. Okay, so if we're doing something like this, I guess firstly we want to talk about the roots alpha, beta, gamma, and delta. Yeah. Now minus b over a, which is minus 5 over 3, that's going to equal minus b over a is going to be the sum of the roots, and we call that the sum of alpha. Yeah, but really that means obviously alpha plus beta plus gamma plus delta. You just kind of need this shorthand in this kind of question, because otherwise you start to go crazy with how many alpha, beta, gamma, deltas you wrote down. Okay, c over a, which is minus 7 over 3, is the sum of the product pairs, which we denote as alpha beta sigma. And that means, and there's 6 different terms to write down here, but alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta. Now, did I say 6 pairs there? I think I did. I think so, hopefully. So that's that one. And then you get minus, I've just made a mistake. I've just seen a mistake. Look at this. X to the 4, x cubed, 0x squared, and then a number times x and then a number. So actually, this should equal 0 because that would be your c over a. Your c is 0. So this equals 0, I beg your pardon. And then minus 7 over 3. Yeah, because we get minus b over a, so that's minus 5 over a. C over a, well, that's 0. And then minus d over a, well, that's actually going to be positive 7 over 3, isn't it? Because minus d over a is positive 7 over 3. And that will be the sum of the triplets, alpha, beta, gamma. So there's 4 terms in that one. You can see each time one of the roots is left off. And then, so minus b over a, c over a, minus d over a, e over a. So that's just going to be 6 over 3, and that's going to be them all multiplied together. Yeah, alpha, beta, gamma, delta. And so that equals 2. Okay, I like writing those down nice and clear. Actually, let me just quickly simplify 6 over 3 to 2, and then we're all good. Okay, so you can see my working down here. Actually, this is what the working I did earlier. I've already written all these down. I don't know why I've written that again. And I've pointed out that there you can see the full expansions. That's the sum of alpha, beta, sum of alpha, beta, gamma, and so on and so forth. Let's make sure that's obviously equal to 2. So, in order to work out this first one, I thought this one doesn't look too bad. I know that if I want to get alpha squared plus beta squared plus gamma squared plus delta squared, if I take alpha plus beta plus gamma plus delta all squared, I draw out a little grid here, and then I don't have to fit it all in because I quickly see what's going on. You get the alpha squared, beta squared, gamma squared, delta squared, but then you need to take away 2 times, well look, you've got 2 alpha betas, you'll get 2 alpha gammas. If I put an alpha gamma in there, I'll have an alpha gamma in here. You get 2 alpha deltas, and look, you do get all 12, you know, all the 6 pairs repeated twice, if you see what I mean. Look, there's another alpha delta. And there you go. So what we've got here is 2 times the sum of alpha beta. So all we've got to do now is do, okay, I've just written down the answer straight away. Actually, no, I just don't think I've actually finished this question. Look at this, I obviously got asked a question in class or something and just stopped doing it. But yeah, oh no, it is the answer because look, that's actually 0, and so the answer is 25 over 9. Okay, there we go. Maybe I wasn't so bad. I thought I missed out a bit there, but there we go. The sum of the alpha betas was 0. So that first bit, 25 over 9. Well done if you got that answer. Part 2. This one isn't too bad either, because if you look at it carefully, when you add these together, if I can just justify this, shouldn't that be 14 over 7? Oh yeah, no, I have worked that out. Right. Yeah, sorry. Thought I got it wrong there at the end. But when I'm adding together those things, the reason why I'm going to get this is because if you think about it, you need a common denominator. So you'll have 2 beta gamma delta over alpha beta gamma delta for that first term, plus 2, and this one needs a alpha gamma delta, and I'm hoping you can see where I'm going with this now. I'm just going to put dot 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 now, because as you can see, you're going to get the 4 pairs of the triplets. That one, yeah? Did I say pairs? The 4 triplets. You're going to get the 4 triplets here, but twice. Each one's going to have a 2 in front of it. So you're going to have 2 times the sum of the triplets over the product, yeah? Now, we already know the product equals 2, and I believe the triplets was 7/3, wasn't it? So we double that, you get 2 times 7/3 over 2, but that just equals 7/3. So I think part 2's answer is 7/3. Once again, let me know if you think I've made a mistake here. Now for part 3, I did it in 2 different ways. What you can do, and I don't advise this way actually, but it's the way I did it earlier. It was just, I'll just do it like that and just crank out the answer eventually. Because what I tend to do with these is I tend to multiply that together, and then I already know what this multiplies to give because I just swap all alphas and betas for gammas and deltas. So that comes to 9 minus 3 alpha plus beta plus alpha beta. That's when you do that one times that one, 9 times, you know, minus 3 alpha minus 3 beta plus alpha beta. So you get that. Same over here for the other one. And then I can multiply this out, and I don't often get a lot of terms here, and that's why it's probably not the most elegant way of solving this. But if we multiply these out carefully, we're going to get 81 minus 27 alpha plus delta, minus 27 alpha plus, sorry, that's gamma plus delta, minus 27 alpha plus beta, plus 9, that's going to be 9 gamma delta plus 9 alpha beta. And so what I've done here is I've done that times that, that times that, that times that, and then carry on multiplying them together. It's probably wise. Can I make a suggestion here? If you're going to do this, do it in a giant grid like that. That's going to make things a lot easier for you. Like this, 9. To be honest, the screen's not very good for me doing this neatly. And you really do need to be quite neat on these questions, or you can end up making a mistake. But if you do it in a big grid, really neat, you should get all of these terms here, yeah? And then when you collect them, you should see you've basically got 81 minus 27 times by the sum of all the roots, plus 9 times by the pairs, the sum of the pairs, minus 3 times by the sum of the triplets, and then plus 2 at the end, because you've got plus an alpha, beta, gamma, delta at the end. And then if you plug the numbers in, you get 121. Now, you know, it's easy to make a mistake when you're doing that. So here's another way of doing it. Let's do it the other way now. Here's the alternative, yeah? So I'm not going to solve this, no. I'm not going to solve this. I'm just going to go like this. Okay. Because we can think of this as 4 different roots, where the roots are related to the original roots, as like change the sign on the roots and then add 3. So if we look at it like that, yeah, so our original equation was solved with x equals alpha, x equals beta, x equals gamma, and x equals delta. Well, let's change the sign on this. I'm just going to put dot 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 here because I'm just going to write down exactly the same thing. Yeah. Well, if I could have an equation which has these roots, that would be kind of nicer. So let's swap w for 3 minus x. Or in other words, w equals 3 minus x. But if we rearrange that, we get x is 3 minus w. In other words, I'm going to trade all my x's for 3 minus w's. Now, this isn't that much better than the method I just showed you, because it's still quite painful. This is for the people who love binomial expansions. Basically, what we can do now is input 3 minus w in for x. Yeah? So you get 3 minus w to the power of 4 plus 5 times 3 minus w cubed plus minus 7 times 3 minus w plus 6 equals 0. Now, you've got to be confident with your binomial expansions, and it's this first one which is going to be painful. I suppose you do have a calculator, but you're going to have that to the power of 4, and then we're going to do this cubed times this times 4, so that's going to give me minus 27 times 4w cubed, and notice the signs are going to alternate because you've got a minus w to the power of 1 there, and then you're going to have plus 9 times by, that's 3 squared, times by 6w squared. Now that's because I know that this row in Pascal's triangle goes 1, 4, 6, 4, 1, and so I need the 6 here. And then you're going to have minus 3 times 4, because 1, 4, 6, 4, 1, w, and then you're going to have cubed, sorry. Yeah, let's just get this right, because this should be w to the power of 1, I apologise. And then this is going to be w cubed, and then lastly you're going to have plus w to the 4. That's just that first bracket expanded. I've still got to times it by 3. This will be a little bit quicker. 27, same idea, but this time we're dealing with a row 1, 3, 3, 1, and you're going to get 9w times 3 here, and then you're going to get 9w squared after that, and then you're going to get minus w cubed. So it's still painful, there's no easy way of doing it. Minus 21 plus 7w. Look, I'm almost off the screen here. Plus 6 equals 0. So this is why this paper's hard. You know, that's a long one. Students won't like doing a long line of algebra like that. If you simplify that, you end up with 3w to the power of 4 minus 41w cubed. I'll tell you a little shortcut in a second. Plus 207w squared minus 452w plus 363. Now, why did I not need to do all this? You might be thinking, but you don't need to do all that. Some of you are probably screaming at the screen. You don't need to do all that. All that matters here is E over A, because we want the product of these roots. Because we want, if you remember, 3 minus alpha. This equation should have roots. 3 minus alpha, 3 minus beta, etc. Yeah? Remember that. The roots are all of those. And so the product of the roots is going to be 363 over 3, which equals 3 minus alpha, 3 minus beta, 3 minus gamma, 3 minus delta. Now, can you see now that I didn't have to do all of the, work out all of the coefficients? I only needed the last one. So who cares about most of this? I only really needed to do 3 times 81, and then on this one, 27 times 5, and then take away 21 and add 6, because I'm only interested in the term independent of W. This also gave me 121, which made me feel like I probably hadn't made a mistake over there. But that's a nightmare, that one. That last 3 marks is hard. It really is. It's easy to make a mistake in that. You know, it's just an algebraic nightmare. Okay, that's the first 4 questions. I'll return with the last 4 questions where we can decide on how bad the modelling was together. Okay, right, well done though. Thanks for listening. Hope it helps. Let me know in the comments if I made a mistake. All the best. Bye-bye.